alcohols undergo substitution reactions as well. And as we discussed earlier, substitution is completely different than elimination. They don't happen simultaneously with alcohol because the reagents that we use for elimination are different than the ones that we're going to use for substitution. We're still going to use an acid in order to perform the reaction since we need to protonate the oxygen in there. So the acids that we're going to use now are going to be different than the ones that we use for elimination because those acids, they need to generate a nucleophile for the substitution reaction to happen. Whether we are using Bronson and Lowry acids or Lewis acids in there, you can easily see the difference between now elimination and substitution. So if I'm using any of those Bronson and Lowry acids, all of these acids, HI, HBr, and HCl, will generate a nucleophile, which is the I minus, Br minus, and the Cl minus that is going to finish up the substitution reaction. Now, HCl is going to be the least reactive among all of these acids. This is why we would need to use a catalyst with HCl. So zinc chloride is just to speed up the reaction. It's not going to show in the product. You're going to generate it back in the product. With respect to the substitution, again, it is type of alcohol driven. So to determine if the reaction goes by SN1 or SN2, you have to look at the type of the alcohol that you are working with. Primary methyl alcohol, these go by SN2. Secondary and tertiary, they go by SN1 reaction. Now, Lewis acids are always an exception because Lewis acids, they go, as we saw earlier for elimination, that the Lewis acid went only by E2 elimination for all types of alcohols. This one over here, the Lewis acid, we have two of them, phenyl chloride and phosphorus tribromide. They're going to go by SN2 reaction only. It is alcohol driven, type of alcohol driven. So since it is an SN2 reaction, it will not work with a tertiary alcohol. So pay attention. If you start with tertiary alcohol with any of these Lewis acids, there will be no reaction. Other than that, primary, secondary, or methyl alcohol, then yes, these are gonna work with Lewis acids. So let's go ahead and have an example over here. So we're starting with HBr, and the first step is going to be always the protonation of the oxygen, and the Br is going to leave. Every time you make a bond, you break a bond. The oxygen is the nucleophile, and the hydrogen here is the electrophilic site. So always your reaction is going to be from the nucleophile to the electrophile, and the bromine is going to leave. So first step always, whether you're doing elimination, whether you're doing substitution, is always the same. The reagent is always having an acidic hydrogen, or it's an acid somehow. It has an electron deficient site. So we protonate, we make the OH a better leaving group. So now, after we make the OH a better leaving group, remember that your mechanism here is going to be an SN2 because the type of alcohol that you are working with is a primary alcohol. And we know that SN2, it is a one-step reaction. So the bromine that left here, this is going to be a good nucleophile. Immediately, that bromine is going to come and attack the sp3 hybrid carbon. The attack for substitution is always going to be on the sp3 hybrid carbon, which is the carbon that carries the leaving group. So here in this case, if you have a chiral center, here you don't. But if you have a chiral center, make sure to consider the stereochemistry, which is the inversion and configuration. The bromine here attacks, the water is going to leave, and I'm going to end up getting a simple substitution reaction. So what I did here is I substituted the OH by the bromine, and water was my leaving group. Let's go ahead and consider if we have a chiral center in this case. Here I am having an example of a secondary alcohol. First here, it was a primary alcohol. The mechanism proceeded by an SN2 mechanism. Here now it's a secondary alcohol, so the mechanism is going to proceed by an SN1 mechanism. I'm starting with a chiral center, so I need to consider stereochemistry throughout. And pay attention and remember that substitution SN1 is carried always by racemization. So you get inversion and retention in configuration. You get two products in this case. So the first step is as usual. The lone pairs are going to come, they're going to attack the hydrogen, and the iodine is going to leave. So it is the protonation step. Notice what I did in the first step. I did the protonation, and I did not break any bond that is connected to the chiral center. So I'm going to end up having the same configuration for this carbon over here, which is going to be an R configuration in this case. Or actually, all I did over here is just I protonated the oxygen by simply adding a bond to this oxygen in there. I did nothing to the chiral center bonds. They are still the same. So that is going to be step one of the reaction. Then water is going to leave since it's an SN1 reaction, and I'm going to create my carbocation. The max that we can form is a secondary carbocation. Now we're going to go ahead and get the second step of the reaction. The second step of the reaction is the iodine, is the nucleophile in the solution. And because we have a potential chiral center now, because this center has three different groups around it, and if I add a fourth one, it's going to be four different groups, so it will be a chiral center, then you need to consider the stereochemistry that iodine is going to attack either from the top or from the bottom, because this is a planar geometry carbon. So if iodine attacks from the top and there, the configuration is going to be the same as the one that you started with. So we're going to call this retention, and iodine attacking from the bottom, that is going to be inversion. These two, if you combine them together, these are racemic mixture. The reason why they are racemic mixture, because there's a rule in organic. If your reactant, which is here, this is the reactant that made the products. If your reactant is optically inactive, then your products, they have to be optically inactive. And if your reactant is optically active, then your product have to be optically active. Let's have an example with the Lewis acid. So we said that Lewis acid, thionyl chloride, or phosphorus tribromide, both they go with SN2 reactions only. So these are SN2 only. And the type of alcohol that I can start with is either a primary, a secondary, a methanol, and not a tertiary. This one is a secondary alcohol, so the reaction proceeds. But if it was a tertiary, pay attention, then the reaction will not proceed. Because it's an SN2, notice that the reaction is going to proceed by inversion and configuration. So the chlorine from the SOCl2, that is going to attack from the opposite side of the OH. So it's going to be at the back. So the reaction is going to proceed again by inversion and configuration. This reaction requires the use of pyridine. Pyridine is a base. And normally pyridine, we use it in these reactions, especially whenever the reagent has a chlorine in it, so that to capture any HCl in the solution. HCl is a very nasty acid, and that acid needs a base to be captured. So this is why pyridine is a must in these types of reactions to use. The Lewis acid for the thionyl chloride is this one over here. This is the electron deficient site. The oxygen is the Lewis base. So you start by making a complex between the oxygen and sulfur, introducing a plus charge, and here you go, you got your good leaving group there. So this one is going to be a very good leaving group in here. And now the chlorine is going to be our nucleophile in the solution that is going to attack in the SN2 mechanism step. So this is an SN2. It's a very fast one. It is a one step. This is a good leaving group. So the chlorine now is going to attack from the opposite side of the leaving group. Again, notice here what I did. When I did the protonation, I did not change the stereochemistry of the OH. The alcohol stereochemistry was in front. The leaving group here is going still to be in front, because all I did is I made a bond between the oxygen and the sulfur. I did not break the bond between the chiral center and the oxygen. So now the chlorine is going to attack from the opposite side. The leaving group is going to leave, and you're going to get inversion in configuration. This is the only product that you're going to end up getting. Now, the leaving group is going to be this guy over here, and the leaving group is pretty much unstable. So this guy is going to dissociate into HCl and sulfur dioxide. And HCl, as we mentioned, it's a very nasty acid, very nasty acid. So this is why we use a base to capture the hydrogen of the HCl. So that base is going to come, take this acidic hydrogen, form a double bond, and the chlorine is going to leave. So now instead of having in the solution HCl, which is a nasty acid, HCl, which is a nasty acid in the solution, you have a pyridinium chloride in this case. This captures the hydrogen and the Cl together with the sulfur dioxide. These two are two byproducts, and this is the organic product. It's okay, you can opt those out. You don't have to show them in the product, but just know that they are there if you see them. Let's have another example with phosphorus tribromide. It's exactly the same thing. You have the phosphorus, which is the electron deficient site. This is going to be your Lewis acid. So the first step, you are protonating the oxygen and making this thing a good leaving group. So once you have a good leaving group, now with phosphorus tribromide, no need to use pyridine. The reason why we don't use pyridine because we don't have HCl, a potential HCl that is forming in the solution. Every time you have an HCl that forms in the product, you will need to capture that. Other than this, you don't need to because there is no possibility here that we're going to go ahead and form an HPR. So what we're going to do over here is a simple reaction where your nucleophile now, which is the bromine that left from the first step of the protonation, now it's going to come and it's going to attack the carbon, and your leaving group is going to leave. Now again, this carbon is not a chiral center, so just opt the stereochemistry out. There is no stereochemistry, but if it is a chiral center, then the reaction is going to proceed by inversion in configuration. Another method to make the OH a better leaving group is to change it into an OTS. In this case, and in this case only, if you're able to change the OH into the OTS, then you're no longer going to work with the rules of the alcohol for substitution or elimination. You are going to work with the rules of the alkyl halide, because remember that OTS, OMS, those go with the rules of the alkyl halides, so substitution and elimination can happen simultaneously. So we're going to start over here with an alcohol, any type of alcohol, because all what you're doing here is you're changing the OH into the OTS. So the O's stays. All what you're doing is changing the hydrogen or replacing the hydrogen with the TS group. This is what you're doing in this case. So to do this, the reaction is an acid-base reaction. Precisely, it's a Lewis acid, Lewis base reaction. So we're going to start with our Lewis base over here, which is the oxygen. This is going to be the Lewis base in there, and the sulfur is going to be our Lewis acid. Now we agreed that the whole thing here, all of that, is going to be called the tosyl group. This is the TS group in there, all of that in here. And the tosyl together with the chlorine, we call it a tosyl chloride or a TSCl. This is para-toluene sulfonum chloride. You're going to see the TS chloride in its abbreviated form, either in front of the arrow or above the arrow. This reaction also requires the use of pyridine because you will be generating HCl in the solution, so pyridine will capture the HCl. So it proceeds by a regular Lewis acid, Lewis base reaction. And the reaction proceeds as follows here. The lone pairs on the oxygen, which is a Lewis base, are going to come and attack the electrophilic site of the sulfur. And then the chlorine is going to leave. So what you're going to end up having is a hydrogen over here with a lone pair and a plus charge. This is what you're going to end up having. You're going to end up having a complex in this case. And now the pyridine role is to come, and of course the Cl minus in there. So you're going to end up having your Cl minus over here. And then the pyridine role is going to come, and we know that this is a base. And we know that this guy over here is an acidic hydrogen. So the base is going to come, take the acidic hydrogen, form a lone pair, and the chlorine is going to couple with the pyridine. So you're going to get your pyridinium chloride in this case. So you're going to end up getting your nitrogen over here. This is my hydrogen. This is a plus charge. Pyridine over here. This is a positive charge in there on the nitrogen. And then you have your chlorine. It is a positive charge on the nitrogen because pyridine has 3 double bonds. So you have a double bond here, a double bond here, and a double bond here. So definitely the nitrogen will have 4 bonds. So the nitrogen will be a positive charge in this case. And this is going to be the pyridinium chloride that is going to form with the product. So your product here is going to be an OTS in this case. And the oxygen will have 2 lone pairs after the pyridine comes and takes that acidic hydrogen over here. So this guy is an excellent leaving group, and we've talked about this in chapter 7. So it's an excellent leaving group, and it behaves exactly like halides. So the reaction can undergo substitution and elimination simultaneously, depending on the type of the nucleophile and the base that you are using. Let's go ahead and have an example in here. Now, these types of reactions, whenever you are changing the OH into an OTS, those require more than one step. So you change it into an OTS, and then you use a second step in order to do either a substitution or an elimination reaction. So here I have a 2-step reaction. My first step is I am reacting the OH with the tosyl chloride in presence of pyridine. So it's going to proceed exactly as we explained. Chlorine is going to leave, and you're going to end up getting your OTS in this case. Of course, I missed the step where I'm doing the protonation in here, because since you have your pyridine immediately is going to come and it's going to take that acidic hydrogen in there and form a lone pair. So it's going to be pyridinium plus charge, and then immediately the chlorine is going to balance that. So you're going to end up getting your OTS in this case. What did I do? I replaced my hydrogen. This is what I did. I replaced my hydrogen with the TS. This is what I did. So the bond that are connected to the chiral center, they stayed the same. I did not break the CO bond. The CO bond stayed the same. All I did is I made a bond between the oxygen and the TS in there. This is what I did. So this bond stayed the same. So the chiral center stays the same. The first step in the reaction proceeds by retention in configuration. Nothing is going to change to the configuration in there. After this, let's see the second step. Now, since this is an OTS and I'm using a CN minus, we know that CN minus proceeds by substitution only. This goes by substitution only. Please review the rules for substitution and elimination of alkyl halides. So the CN is a strong nucleophile. This guy over here, it's a strong nucleophile in there. So it's going to proceed by SN2 only. There is no elimination with the CN. So the CN over here is going to come and attack from the opposite side of the OTS. OTS is on the right. So the CN is going to attack from the left. It's in plane on the right. So the CN is going to be in plane to the left in there. So they can proceed by inversion and configuration. So you're going to see it over here. Nothing is going to change to the CH3. The CH3 is going to stay behind. The hydrogen is going to stay in front, but now the CN is going to be in plane to the left, and the reaction is going to proceed by inversion and configuration. My point here is that the final product for this reaction is going to be an inversion in configuration. This is going to be the final product of this reaction. Whether I am starting with a primary alcohol, a secondary alcohol in there, or a tertiary alcohol, the first reaction happens in there. But pay attention, because tertiary alcohols, they have no reaction with the second step. They have a reaction with the first step, but they don't have a reaction with the second step. So here I included that, or tertiary alcohols, but if the tertiary alcohols are present, then they will not. There will be no SN2 in the second step. And especially if you're using the CN minus, this doesn't go by elimination. It goes only by substitution, because this one is going to be a strong nucleophile, but it is a weak base. So it doesn't go by E2 mechanism. It goes just by SN2, so you will have no reaction in the second step. Let's have another example over here. So first step is the tosyl chloride. So all I'm doing is that I am replacing the hydrogen with the OTS. I am keeping the same stereochemistry of the OH. This is in front. The OTS is going to be in front. So the first step is going to proceed by retention and configuration. Since this is a secondary alcohol, I can simply perform the substitution in the second step, if there is a substitution. So now I'm doing the NaOCH3. Now, since I'm doing NaOCH3, now I know that the OR is a strong nucleophile and it is a strong base at the same time. So the reaction is going to proceed by substitution and elimination. If it is substitution, it's going to be SN2 because it is a strong nucleophile. Again, please review those reactions because they are very important in chapter 7. So the OCH3 is going to attack from the opposite side of the OTS. So the reaction is going to proceed by inversion and configuration. This is SN2. And then you're going to have your elimination in there. Notice that, or remember that elimination E2 happens whenever your hydrogen and the OTS, or the leaving group, they have to be anti-periplanar with respect to each other. So here I have two hydrogens here, and two beta hydrogens in there. What you need to look for is the hydrogen that is opposite to the OTS. So I'm looking at the hydrogen which is at the back here. This is opposite to the OTS, and this is opposite to the OTS. It needs to be anti-periplanar with respect to the leaving group. So I'm choosing the hydrogen at the back and not the hydrogen in front. You're going to end up getting your double bond on this side and your double bond on the other side once your elimination happens in this case. Now, if I want to consider which one is major, both of those are di-substituted alkene. So, but however, this double bond over here is closer to the CH3. So this one is going to be major, this one is going to be minor, but you can put both as major products because both are di-substituted alkene. Guys, remember that OTS is a better leaving group than any of the halogens in there. The reason why, because it comes from a stronger acid than any of the halogens. And whenever you make the OTS, forget about the alcohol rules, and now you are back to the alkyl halide rules. Whatever worked with alkyl halides is going to work with the OTS. This is going to be the sum of both the steps in there, and this is how you're going to see it in your problems and in your homework. There are additional examples in the notes. Please go over those. Also, there are examples in the problem set that I posted for this chapter. Go over those as well.